Welcome to this presentation in the series, Electronics, the Story of One Human Lifetime by David Beams and Gary James. I am David Beams, Associate Professor of Emeritus of Electrical Engineering at the University of Texas at Tyler, and I'm calling this presentation Something They Never Told Me About in School. And that something was digital signal processing. Now, digital signal processing, it is difficult to overestimate its importance to electrical engineering today. It underlies Wi-Fi, cell phones, GPS. But at the time that I was an undergraduate, well, it was still in the cutting edge research stage in the early 1970s, and it certainly was not in the undergraduate curriculum anywhere. A lot of things have changed since those days. For instance, I was a sophomore already when Intel introduced the world's first microprocessor, the 4004, in 1971. And when I finished my BSEE, digital design was still dominated by TTL, particularly small scale and medium scale TTL devices. And the 741 op-amp, venerable as it now is, was cutting edge at the time. It had only been introduced maybe about 6 years before. Point. You can't learn everything you're going to need for a career of 40 plus years in 4 years of a bachelor's program. You have to keep learning new things, teaching yourself new things, finding new information. I had very little to do directly with DSP in my career, but I was curious about it and I tried to learn about it. But reading it, just simply sitting down and reading about it, was not a very efficient way to learn about it, though, because, well, the literature was full of unfamiliar nomenclature and symbols. What I read was often theoretical and abstract. Well, I can appreciate theoretical and abstract up to a point, but I'm an engineer. I always understood things better when I could see concrete examples with numbers. Now, disclaimer, I am not an expert in DSP. I am not an expert in the mathematics underlying it, but I did learn some useful techniques along the way. And this presentation is about a practical technique for designing digital filters from a continuous time prototype whose electrical behavior we want to emulate. And it uses a form of mathematical wizardry that's known as the bilinear transformation. So let's begin with this, just a little bit of theory. The Z transform, as it's known, and the bilinear transformation. Let's start with the time shift theorem of the Laplace transform. If I have a function f of t, its Laplace transform is f, capital F of s. But if I shift that function in time, then that multiplies it by this exponential. So f of lowercase t minus time shift interval capital T equals the Laplace transform of f of t multiplied by e to the minus st. Now this is kind of mathematically messy, so somebody got the idea to designate z as e to the st, which e to the minus st here becomes z to the minus 1. Now, our design process begins with a continuous time transfer function in the Laplace transform variable s. But what we're going to do with our continuous time transfer function h sub a for analog is we're going to substitute a relationship relating z to s as the argument of h sub a. And from that, we will get h sub d of z, which is the discrete time transfer function. Okay, let's redefine z as e to the st over 2 divided by e to the minus st over 2, which you'll agree that's equivalent to this expression. Now what we'll do is we will expand the numerator and denominator both in terms of power series. And now let's truncate the power series, keeping only the constant in the first order terms in the numerator and denominator. And with a little algebra, we can find s as a function of z. This is our g of z, which you're going to use as this argument. This mapping is known as the bilinear transformation. Let's start now with a first order continuous time transfer function, a generalized first order continuous time transfer function. Now we're going to replace S by its bilinear transformation representation. Then we'll multiply each term by the quantity z plus 1, just to put everything over a common denominator, numerator, and to put the numerator and denominator each over a common denominator. And then we'll collect terms. And now we have our discrete time transfer function in terms of the z transform variable z, and in terms of coefficients from the continuous time transfer function and the sampling interval. Now, the last step we're going to take here, we're going to make the greatest power of z in the transfer function to be 0 for causality purposes. Z to negative powers represent shifts from the past into the present. Z to a positive power would represent a time shift from the future into the present, which would violate causality. So now we can derive output and input polynomials from that transfer function, where y is a polynomial in Z representing the output sequence, and x is a polynomial in Z representing the input sequence, and then cross-multiplying gives us this expression, which I can rewrite in terms of in the time domain by invoking the inverse Z transform. And what we have here now is the difference equation that describes the discrete time system. Y sub n is the current value of the output. Y sub n minus 1 is the previous value of the output. X sub n is the current value of the input, and x sub n minus 1 is the previous value of the input. And the coefficients that multiply them are calculated from coefficients of the continuous time transfer function and the sampling interval. So far, so good. So let's define some constants now to make these expressions more compact. Defining constants alpha 0, alpha 1, beta 0, and beta 1. And using these constants, then we can write the difference equation in this form, and I've normalized the constant of y sub n to be 1 by simply dividing every term by beta 1. And if we want to, we can write an expression for the current value of output y sub n based on the current input x sub n, the previous input x sub n minus 1, and the previous output y of n minus 1. And this is a multiply accumulate structure that we can implement directly in software or on a dedicated DSP chip. Now, we'll follow the same steps for a second order system. Generalized second order continuous time transfer function, replacing S by the bilinear transformation, and mathematical manipulations to put things over a common denominator and collect terms, and defining the transfer function in terms of output and input polynomials. And then we will define some new constants, or the new constants we've introduced, alpha 2, alpha 1, alpha 0, beta 2, beta 1, beta 0. We'll define those. And now we can write the difference equation. Difference equation representing that generalized second order continuous time system. So finally, if we want to, we could write an expression for the current value of the output in terms of the current value of the input and previous values of the input and previous values of the output. We're almost there. The importance of these derivations, by the way, for first and second order filters is that we can make filters of any even order length by cascading second order sections. And if we add one first order section, we can make an odd order filter, again, of any length. So we're almost at the point where we can design digital filters from their continuous time versions. There's just one more thing we have to consider. It's the phenomenon that's known as frequency warping. Mapping the poles and zeros of the original continuous time transfer function to the discrete time transfer function is exact if we use the definition z is equal to the e to the st. But mapping from s to z is not exact with the bilinear transformation because truncation of the power series. But by pre-warping the continuous time transfer function, we can ensure that the discrete time poles and zeros are properly placed, and so we get the frequency response that we're looking for. Let's see how that works. Let's start by considering sinusoidal steady state analysis, in which case S equals J omega sub A for analog, and Z is E to the J omega sub D T, and we'll equate S to the bilinear transformation and make appropriate substitutions for sinusoidal steady state. Now we'll multiply this expression by e to the minus j omega dt over 2, numerator and denominator both. There's method in our madness here. So with this small further amount of math, we get the relationship between omega sub A and omega sub D. Now, as a note, the tangent function here, if the argument to the tangent function is less than around 15 degrees or pi over 12 radians, the argument of the tangent function and the tangent function are essentially the same. That is, tangent of theta is approximately theta if theta is less than or equal to around pi over 12. And if this argument is small, and I can just simply eliminate the tangent function, then we see that omega sub A and omega sub D become one and the same. It's confused? Okay, let's do some concrete examples. And we're going to start by designing a first order low pass filter with a cutoff frequency of 1 kilohertz. And we're going to assume a sample time of 25 microseconds. This is the continuous time low pass transfer function with a cutoff frequency of omega sub A. Let's do the frequency warping. And we get omega sub A should be at 29 or 6296 radians per second. Instead of 2 pi times 1,000, it's a little different. The frequency warped continuous time transfer function then is this. And now let's match coefficients of this expression to a generalized first order continuous time transfer function. And we see that A1 here is 0. A0 is 6296, B1 is 1, and B0 is 6296. Now we're in a position to calculate the difference equation. Here again are the coefficients of the general first order continuous time function. And we calculate the coefficients alpha 1 and alpha 0, beta 1 and beta 0. And the general first order differential equation, to refresh our memories, is this. And making the numerical substitutions, here we have our specific difference equation for that first order filter. Now, if I want to, I can describe the current value of the output based on current and previous values of the input and the previous output, like so. A quick sanity check. If the input sequence is a string of ones, meaning it's a DC input, the series for y sub n converges to 1, which we would expect. Well, let's see how to verify this with MATLAB or Octave. Well, we'll see that, but we'll postpone that for the time being. For now, I think I rolled the wheel backwards. It's break time. So come back when you're ready. I'll be here. Okay, we're back. Let's do a second example. A bandpass filter with a peak gain of 5 at 500 hertz and the Q of 10. Let's use a sampling interval of 50 microseconds. Here is the continuous time transfer function for a bandpass response with a peak gain of H sub 0 at a frequency omega sub 0. Let's do frequency warping. and omega sub 0. If the design value omega sub d is to be 2 pi times 1,000, we need omega sub naught in the analog transfer function to be 3148 radians per second. So here we have the continuous time transfer function with numerical values. I've repeated that continuous time transfer function here. And let's map coefficients to a generalized second order transfer function. And we can see that A2 is 0, A1 of the generalized transfer function is 1574, A0 is 0. We have B2, B1, and B0, which we can read from this continuous time transfer function. And now we can calculate the coefficients for the difference equation, and we're going to use these coefficients taken from the continuous time transfer function, which I've repeated here for our benefit. Here's A2, A1, A0, beta 2, beta 1, and beta 0. And so now we can finish calculating the coefficients for the difference equation. And here we have the difference equation representing this bandpass filter. Now the following code computes the frequency response of the first order low pass filter. I'm not going to show you the process for doing the second order bandpass filter, but it's very similar to doing the first order filter. You should be able to figure it out. Well, let's go through the first order filter here step by step. We're going to define here first an array of the coefficients of x sub n and x sub n minus 1 from the difference equation. Here are the coefficients of y sub n and y sub n minus 1 from the difference equation. Sampling interval we'll set at 25 microseconds. And we're going to create an array of frequencies at which to evaluate the frequency response from 10 hertz or 10 to the first through 10 kilohertz or 10 to the fourth, a logarithmic array, and we'll use 512 points. Octave, if you allow Octave to choose the frequency range over which it evaluates the performance of a discrete time filter, its default value of number of frequency points is 512. Why 512? I don't really know, but we'll just go with what they do. And now what I'll do here is I'll define an angular argument range to the frequency response function we're going to invoke in a moment. We're going to make that 2 pi times the frequency range f1 times the sampling interval. And this is the command that does the work. This computes the frequency response of a discrete time system in terms of its difference equation, its coefficients of the difference equation over this range of frequencies, and assigns it to a complex variable, which I've here called h1. And here I calculate the magnitude of h1 in decibels. And here I calculate the phase in degrees. The arctangent 2 function is a 4-quadrant arctangent function, which returns a result in radians. I want to see degrees, so I'll invoke the rad 2 degree function. And the following octave code now graphs the magnitude and phase responses of that first order low pass filter. Again, the gain is in decibels, phase is degrees. So I create a new figure and I ask for a semi-log plot, which plots a logarithmic x-axis and a linear y-axis. And I'll plot frequency, gain in decibels, and I'll add some labels and a title. And now I'll create another figure for the phase response. I'll plot the phase response, add labels and a title. And let's see what we got. Here is the magnitude response plotted with Octave. And just for comparison, even though I didn't show you the code for it, I have plotted on the same set of axes. The dotted blue line represents the magnitude response of the continuous time or analog filter. And you can see the two match quite well up into a range, into frequencies of several kilohertz, and -3 decibels occurs at 1 kilohertz. Looks pretty good. Let's check the phase response. This is the phase response. And even though, again, I did not show the steps for how to compute the magnitude response of the continuous time filter, I've done it, and I've plotted the results on the same set of axes with the digital filter. Here's the phase response of the discrete timer digital filter, the red trace, and the original unwarped, shall we say, analog filter, the filter we hope to emulate in the first place. And let's see, at 1 kilohertz, the phase passes through -45 degrees on each. I'd say that looks pretty good. So I will show you here now. I'm not going to show you the Octave code, but here's a plot of the bandpass gain response. And here I have shown both the digital and the analog or digital and continuous time filter responses. And notice the peak is right at 500 hertz. The gain is 14 decibels, which is 5. Got that. And if I look at the -3 dB frequencies, that should be about here and here. Those two should be separated by a value equal to the center frequency divided by the Q, and we're aiming for a quality factor of 10. So we should get a width between the two -3 dB frequencies of approximately 50 hertz, and just a quick eyeball of the graph shows that it looks pretty good. So I'm going to show you here another second order example, but I'm going to skip over all the steps. I'm going to go right to the difference equation and see if you can follow the cookbook procedure and come up with, see if you get the same difference equation that I did. So example 3 here. We'll take the bandpass filter, and now we're going to turn it into a band reject or a notch filter with a minimum response at 500 hertz and a Q again equal to 10. And for grins, we'll change the sampling period to 100 microseconds. Here is a continuous time transfer function for a band reject filter with a notch at omega sub 0. And cranking through all of the steps, this is the difference equation. So work through the calculations and see if you get the same result. And I think you should, because if we graph the magnitude response of the digital notch filter, this is what we get. I didn't graph the continuous time filter on the same set of axes for comparison, but trust me, they're very close. And let's check something here. -3 decibels would appear to be about here and here. And the frequency separation between the two -3D points is around, looks like around 50 hertz. And the notch frequency divided by Q in a notch filter gives you the separation between the two, or the width, the band width between the two -3 dB frequencies. This looks pretty much like we would expect it to. Now, one thing that I want to point out here, and I should have pointed out on that previous frequency response plot of the bandpass filter, is you notice here that I've used a linear frequency scale. When you're plotting the frequency response of a highly frequency selective, a high Q circuit of some kind, it is better to display the response over a narrow range of frequencies using a linear scale, so you can accurately see the min or max response, as opposed to using a wide range of logarithmically spaced frequencies. So notice here, the frequency response is from 400 to 600 hertz. And I did the same thing with the bandpass filter. I just simply forgot to mention it to you. But anyway, the method works. In this presentation now, it's not rigorous. I've jumped over a lot of details, but it gives a cookbook type of approach to designing first and second order digital filters from their continuous time prototypes by means of the bilinear transform. It's not a rigorous mathematical exposition of the properties of the Z transform. I have jumped over a lot of mathematical niceties and said, this works. Again, engineer. But again, how about designing higher order filters? Well, we said earlier that we could cascade second order sections to produce an even order filter of arbitrary length. And if we add a first order section to it, we can produce an odd order filter of arbitrary length. I will do an example, a design example of a complex higher order filter in a subsequent presentation, but I think we've absorbed enough for now. So thank you for exploring the world of electronics with us, and see you in the next presentation.